Hi students, let's see another application of Gauss's theorem. This time the question is derive an expression for the electric field intensity at a point near a thin infinite plane sheet of charge density sigma. So by using Gauss's theorem, we need to find electric field at a given point because of this infinite plane sheet of charge density sigma. Now this plane sheet is also a symmetrical object. So if it's the symmetrical object with charge, so we can easily apply the Gauss theorem. So let me write first what is given there. So given to me, given that a thin infinite plane sheet of charge density sigma. Suppose if I wish, I would like to show in figure, yeah, this is the setup which they are given. Infinitely plane sheet of charge density sigma. Now what is my task? Here the task is to find the electric field at a distance r due to this sheet, due to this thin infinite plane sheet. So if this is the object, so we always cautious about our useful Gaussian surface. So here what is my useful Gaussian surface? So this Gaussian surface is a clever selection for this infinitely plane sheet object. If we select such a surface, that surface help us to find the electric field very easily. So that is the always a matching between the symmetrical object, charged object what we selected and the Gaussian surface what we pick up. If these two matches perfectly, so our problem will become handy. So here my Gaussian surface in this case also a closed cylinder with end caps of area A. So in this case also I am taking a Gaussian surface and those Gaussian surface as a cylindrical Gaussian surface just like cylinder, and the cylinder having the two ends area. Suppose if I wish, I would like to show how we can draw a Gaussian surface. That once, yeah, this is my present infinitely plane sheet of a charge along with Gaussian surface. So here you can clearly observe this is a infinitely plane sheet, infinitely charged plane sheet. Okay, to this sheet, and our clever selection is Gaussian surface. Now here you can see, closely observe, this is the Gaussian surface. This Gaussian surface is pierced two sides, from one side to another side. Suppose if you want to find electric field this side, let me mention as a P dash, you can take this open surface, this is the one face and this is the another face. So that will be the two surfaces you have to take. Suppose you want to find electric field in this side at a point P. Now you have to consider this is the Gaussian surface of area A and the starting also. So these two areas we need to consider, because at this surface only the electric field lines are started to come. So that's why in this case the clever selection of the Gaussian surface is a cylindrical Gaussian surface with open ends of area A. Suppose you would like to see the cross-sectional view. It means how it would look like. Just you can concentrate this picture again at here. Now instead of keeping the sheet like this, now the sheet is straight like this. Now this is my Gaussian surface area. So the Gaussian surface which is highlighted at here. Now this is a cylindrical Gaussian surface. Now how the electric field lines are coming? Electric field lines are started to come from this side. So now at here, from the surface. So in this figure, so this is the region. Now it is already having another surface. So this is the point. So this is a cross-sectional view of the same infinitely thin sheet with a Gaussian surface. Now our task is to find electric field at a given point. So for that, I would like to take this figure same as it is. So first I need to write my Gauss theorem. So the Gauss theorem says to me that the closed integral of E bar dot ds bar equal to Q by epsilon naught. So this Q equal to charge enclosed. Now in this theorem, first I wish find what is my total electric field. So this is also nothing but flux. To calculate flux, at a point P, I would like to calculate at this point. Now at this point, clearly I am seeing two areas. So if I can highlight the areas in the figure. So this is the area you are seeing. This is the surface area of the cylinder of the end point on the right side of the, and this is the starting area. Now if you mention that this is surface area S2 and this surface area S1, so I can write the total surface. So closed integral of E bar dot ds equal to closed integral of E bar dot ds1 plus closed integral of E bar dot ds2. They both are two different surfaces. So we located the surfaces. Now our task is to find the surface area direction and electric field direction. Suppose if I mention the electric field direction on the surface S2, so this is the electric field direction with the green arrow. On the surface S1 also, the electric field direction along in the same direction. Now we need to mention area direction. Suppose if you can take the area direction, and the area direction also it shows the same direction. which is the purple arrow at here. So on the surface S1, so it is also electric field, and area they both are having in the same direction. If they both are having same direction, we can write E bar dot ds equal to the closed integral of E ds having surface area A E times dA cos theta plus closed integral of E times dA, sorry it's not dA, it's only A, E times A cos theta. Why? Because here ds1 equal to ds2 equal to the area A. And what is the theta? The angle between electric field vector and area vector equal to 0 degree, because they both are showing in the same direction. Now you can get the total area, so you can get the total electric flux integral of E bar dot ds equal to, so this will becomes 2 times E bar dot A. Now if this is the total flux, and we need to make it equal by using Gauss theorem, which is equal to Q by epsilon naught. So since Gauss theorem, the closed integral of E bar dot ds bar equal to charge enclosed upon epsilon naught. So in the place of E bar dot ds, so I can substitute in the place of this value. I just calculated what is total. So here it will gives to me 2 times, so E dot A, which equal to charge enclosed by epsilon naught. Now if you can see, the given object is a thin sheet. Thin sheet, we can calculate the charge as the sigma equal to the charge density, sigma equal to charge per unit area. So for the two-dimensional object, we are calculating this sigma, that is nothing but areal charge density. In the given problem also, they mentioned that it is having the charge density of sigma. In the given problem, they are having the charge density of sigma, which means charge per unit area. So in this sheet, if you can take a small area, so that area if you can highlight, so in this small area, how much charge is present? So the charge is present in this small area equal to, that is sigma, is equal to charge per unit area. So from this relation, I can calculate what is the charge. Charge Q equal to sigma times A. So that is the meaning of charge density. So here, how much is the charge enclosed? The enclosed charge, here it is, the charge enclosed, so Q enclosed equal to sigma times A. Now you can substitute Q enclosed value at here. So now 2 times E times A equal to sigma times A upon epsilon naught. Now you can cut the like terms, both the times area gets cancelled. So the electric field at a point equal to sigma upon 2 epsilon naught. So this is the final expression, the electric field. The electric field due to a thin infinitely charged sheet. A thin infinitely charged sheet. The electric field at a point. The electric field at a point we can write as E equal to sigma upon 2 epsilon naught. So that is my final expression. Therefore, the electric field at a given point due to infinitely charged thin sheet is electric field E equal to sigma upon 2 epsilon naught. So this is the final expression.